Okay, let's look at the kind of problem that we typically solve in Excel. And I want to use this example problem as a way of showing you what good procedures are for working in Excel, for sort of a set of best practices for using Excel to solve problems. So the problem I'm going to solve is a real simple one that involves calculating what's called the porosity n of a porous medium. And the porosity n is defined as the volume of the voids in a sample, the empty spaces, divided by the total volume that includes both the empty spaces and the solids. And the way we can often measure this directly is by taking a sample. And here we have a cylinder sample of a porous medium. Let's say this was stuck into the ground. We collected a sample, and inside this tube we have a mixture of solids and water. We measure the length of the tube L, the radius of the tube R, from which we can calculate the area. We take the sample back to the laboratory, and then we basically drive out all the water by heating it up, so that we end up being able to measure the mass of the solids, the dry mass of the solids, which is shown over here. From the dry mass of the solids and the density of the solids, which is given here, we can calculate the volume of the solids. And from the relationship that the volume, the total volume, is equal to the volume of the solids plus the volume of the voids, we can calculate the volume of the voids and then the porosity n. And that's what we're going to do in Excel. It's a really straightforward, simple problem in Excel. But by going through it, I hope I can demonstrate to you how we can make this process more useful, not only to you, but to anyone you share that spreadsheet with. So let's go to Excel. Here is a blank Excel worksheet, and we're going to use this to solve this problem. So the very first thing you want to do, and the basic idea here is this. Even though you may not think of it that way, when you use Excel to solve a problem, you are essentially writing a computer code. You're using Excel to automate the writing of computer code, and you're having Excel's built-in features and automatic calculation actually run your code. So there's really not much difference between writing clear computer code and writing an Excel spreadsheet. And we can use the same exact principles that apply to good practices in writing computer code to good practices in creating Excel worksheets. And the key idea is to make it as clear as possible what you're doing. So at the beginning of every spreadsheet that's designed to solve a problem, I always describe what the problem is so that if I can come back to it later, I will remember, because I very well might forget. So in this case, let's do that. The problem here is to calculate the porosity n of a cylindrical sample given its dry mass. That's what I'm going to be doing here. Simple, just a one-sentence statement of this is what this spreadsheet is about. The next idea here is that when I name the variables that I'm going to be used, I try to use symbols that are representative of what the variables actually mean. I don't use X and Y and J and stuff like that. I try to use variable names that are meaningful. So in this case, my variables are going to be the radius R in inches. I always include the units as well. They are the length in inches. I have the density in grams per cubic centimeter. Let me just make that a little wider so you can see that. And I have the mass of the solids, the dry mass of the solids in grams. Those were the things that were given. So let's fill these things in here. So the radius as given, let's just remind what this looks like here, was 2.00 inches. Now, that's going to present a little bit of a problem, actually, because if I just write in 2, Excel is going to take that as what's called the general format and just write it as 2, and that will not show me that, in fact, I know this number to three significant figures. So what I actually need to do is consciously change the formatting of this to what's called the number format, where I can adjust the number of digits after the decimal point, and I want to adjust it till I get 2.00. That's what was given. The next thing I'm going to do for all my input data, and there's a lot of ways to do this, but this is the way I like to do it. I like to give it some kind of special symbol to me to know that this was an input data. These were not things I'm calculating. These are numbers that were given by the problem. And the simple way to do that is just to highlight them a given color. I always use yellow. So a yellow cell means this was data I was given. I was given a radius of 2.00 inches. I was given a length of 10.5 inches. And here I don't have to worry about changing the format because it just defaulted to the correct number of significant figures. My density of the solids was 2.65 grams per cc. And the mass dry, I don't remember these, let's take a quick look, was 4,785. Just for convenience, a lot of times I'll change the formats of these numbers so that, what I want to do is allow the thousand separator, that comma. I just think it makes it easier when there's a comma after the 4, and that's something you can either add or not add. And again, all of these were numbers that were given, so I'm going to highlight them in yellow. So this is the problem. These are the data I was given, and everything else I do now is going to be, by inference, a calculated cell. So if I don't have it in yellow, it must be something I calculated. And then I'm going to provide a comment, if it's not obvious, how I did that calculation. So the first thing I'm going to do is I'm going to always work in the MKS system. It's just a habit of mine. So I'm going to convert all these values that are in inches and grams per cubic centimeters and grams into MKS. So the radius in the MKS unit of meters, this is actually a really easy thing in Excel. I'll use the Excel convert function. So this is written as equals convert the value in B3 from inches into meters. How easy is that? The length in meters now will be equal to convert value in B4 from inches to meters. There we go. The density in kilograms per meter cubed, that's the MKS unit. I know that is just equal to B5. They differ by a factor of 1,000, CGS and MKS, so it's 2,650. Once again, just out of habit, I'm going to change this so that I can display the comma after the 2. I just like the way that number looks better. And finally, I'm just doing my conversions now. The mass of the solids in kilograms will equal B6 divided by 1,000. There's that factor of 1,000 again. And I don't have, there we go. It's 4 significant figures. So these, I don't really need to comment on these because it's pretty obvious. They're just unit conversions. So I'm not going to write anything in here because I don't need to. But now let's actually start doing the calculations we need to do for this problem. So the first thing we want to do is let's calculate the total volume. Remember the total volume here, I'll write it down here for a reason. The total volume is equal to the area of the base times area of base times the height L. That's the volume of a cylinder. So the first thing I'm going to calculate is the area of the base. Well, it's just a circle, so it's going to be equal to pi times r squared. Just to remind me, so I can do this now, okay? The area in meters squared is going to be equal to the pi, which in Excel is pi parentheses, close parentheses, times the radius squared. There we go. I know, I mean, in many cases you may say, look, I will always remember how to do area of a circle, but if you forgot, this comment here doesn't really hurt anything. The other thing I sometimes do is I'll move these over. Move these over a column so they don't clutter up my answer. There we go. So that's the area. So now the total volume in meter cubed will equal the area of the base, B11, times the height, B8. There we go. The area, the total volume is the area base times height. There we go. Notice I'm not worried, by the way, about significant figures for any of these intermediate steps. I'm only going to be concerned with significant figures of my given numbers in yellow and when I get my final answer. All right, now the next step is actually maybe a little bit subtle here. I need to calculate the volume of the mass given the volume of the solids given the mass of the solids and its density. Now, that may be something that's really obvious, but might not be. So I'm just going to write down my logic here. Well, if density equals mass divided by volume, then volume equals, volume is going to equal mass divided by density. Right? So in order to calculate the volume of the solids in kilograms, I need to take the mass of the solids in kilograms, there it was, it's B10, and divide by the density in MKS, there it is in B9. Okay, so that now is the volume of the solids. Again, that's the kind of thing that you might have looked, 3 months later, you come back and look at the spreadsheet and go, what did I do there? Having the explanation here will really, really help. It will also help me if you send this to me saying, why did I get this wrong? And I'm looking at your spreadsheet. It really helps me if I can see your comments so I can figure out what you're doing. Okay, so now we're almost there. We need to calculate the volume of the voids. Oops, something, that was a mistake here. The volume of the solids should have been in cubic meters, right? Not kilograms. That didn't make any sense. So the volume of the voids in cubic meters now will simply be, I'll write it out and then I'll show you where I got it from. It's the total volume minus the volume of the solids. And I'll write this here. So if the total volume is equal to the volume of the solids plus the volume of the voids, then the volume of the voids will equal the total volume minus the volume of the solids. That's what I wrote on the right over here, right? Didn't I write that right over here? There we go. So based on this thing right here, we know this is true. Then what I'm saying is that the volume of the voids has to equal the total volume minus the volume of the solids. Right. Okay, so there we have it. So now we have the volume of the voids in B14, and we have the total volume in B12. So that's all I need now to calculate N. And notice I'm not going to put any units here because it's dimensionless. So realize that if I don't have any units, the implication is that it's dimensionless, will equal B14 divided by B12. There we go. This is my final answer then for the porosity. And once again, it really, really helps if you highlight this somehow. I'm going to use a color to show that this is my final answer. That was my goal, was to calculate N. Where is it? Here it is. Okay. Again, I'll comment it just for completeness sake. N equals the volume of the voids divided by the total volume. Now, there's one final thing we need to do before we present this, finish this up, and that is to express the answer in the correct number of significant figures. So what I like, there's two ways to do this. One would be just to go to modify this number in B15 to the correct number of significant figures. But I actually like to just repeat this. Here's N, and it's equal to B15. So I get exactly the same number here. But now, the second time, I will actually adjust it to the correct number of significant figures, which should be 3. There were 3 significant figures in everything here. So I'm actually going to adjust this to 3. Whoa, went the wrong way. Just these little arrows up here. Oh, I know what happened. That's weird. Sorry, this is spreadsheet being really weird for me. These are all numbers now. Okay, so I will, lots of significant figures. And I want this to be 3 significant figures. There it is, 0.165. So my final answer, the answer I would present, fill in on a quiz, is 0.165 or 16.5%. I've highlighted, I've shown it twice here because this is the number in all its full significant figure glory, not that I would present that, and here's the number as I would actually present it, taking into account the significant figures implicit in the given data that are shown in yellow. And now, is there anything else I might need to do here? Probably not. If I wanted to get fancy, I could actually paste in an image of the cylinder that I copied over here to show that the area, the volume is equal to the area times the length. And I might actually end up doing that, even though that's a lot of work for a problem that's quite complicated. But in this case, it's pretty clear that I have a cylinder, so that the cylinder area, the volume of the cylinder is going to be the area of the base times the height. So there's really nothing more I need to do here. I might make a comment here saying, let's see, the density. I might make a comment here, assuming the solids are quartz. Remember I said that in the first part. And this I might say, this is the mass of the solids, mass of the cylinder after all water has been driven off. Just to make that really clear, that's what I'm doing here. See, is there anything else? So that's probably it. So I guess my final point is that the more explanation you provide, the better. And even though adding those comments and thinking about your units and all these other things that I've shown you here may make it take you maybe another 2 minutes or 3 minutes or even 5 minutes to create the spreadsheet, it's going to create a spreadsheet that will have much more enduring usefulness, because now if you come back to this a year from now, you can figure out what you did and correct mistakes you may have made. You can send this to someone. Hey, how do I calculate the density? How do I calculate the porosity of a sample from a sample that I dry out in an oven? You can send them this and they can read it and they can make sense of it and they can figure it out. So the key idea here in terms of best practices is provide lots of comments. Name your variables. So let's actually write these things down. Let's write these down. These best practices here. Let's go here. So these are going to be the best practices. Number 1, use lots of comments. Explain everything you've done so that someone coming back later can figure it out. Number 2, when you use variables, give them meaningful names like R or dense or something like that. Don't use just random letters. Make the variables mean something. 3, really important, always show your units. It's amazing how often I see spreadsheets where students have numbers in there without any units, and I don't know if that unit represents inches or meters or kilometers or miles or fathoms or nanometers or what. So always show your units. 4, always identify what data are given by the problem, which ones are calculated, and always try to highlight the final answer so that it's easy to find. In the example I gave, I highlighted the given values in yellow. Anything that was just blank and not highlighted at all was assumed to be calculated, and the final answer I highlighted in blue. And finally, make sure to take significant figures into account in your final answer. As I did it in the example, I actually gave the final example twice, once with all the significant, intermediate significant figures, and again, the final answer in here in cell B16 with the correct number of significant figures. And if you do that, if you follow those practices, your spreadsheets will be much more useful both to you and to anyone you share them with.